For the project background, offshore oil rigs require efficient and reliable pump control systems to regulate pipeline pressure, flow rates, and oil levels in storage tanks for smooth operations. Maintaining optimal pressure and flow is critical to prevent pipeline failures, pump cavitations, and leaks, which can cause operational downtime and environmental hazard. Oil level monitoring in storage tank is essential to avoid overflows, shortages, and supply chain disruptions. Manual monitoring and outdated systems lead to inefficiencies, delayed responses, and higher operational risk. A PLC-based pump control system offers an automated real-time solution for accurate monitoring and precise control of these critical parameters. PLC technology integrated with sensors and actuators enable automatic pump operation, real-time adjustments, and system optimization without failure intervention. The system uses ladder logic programming to ensure precise sequencing, automatic corrective actions, and reliable data acquisition for improved efficiency. And the final part is enhanced safety, reduced operational costs, and optimized resource utilization are key benefits of implementing a PLC controlled pump system in offshore oil rigs. Next part for the problem statement. Offshore oil rigs face challenges in maintaining stable pipeline pressure, flow rates, and storage tank levels, leading to inefficiencies and operational risks. Pressure fluctuations in pipelines can cause pump cavitation, leaks, or even pipeline ruptures, resulting in costly repairs and production losses. Inconsistent flow rates disrupt oil transportation, leading to inefficient resource utilization and downtime. Poor oil level monitoring in storage tank can cause overflows, spills, or shortages, affecting safety and production continuity. Traditional monitoring systems rely on manual operations or outdated automations, which are prone to human errors, delayed responses, and inefficient performance. The lack of an integrated PLC-based control system increases the risk of unexpected failures, high maintenance costs, and environmental hazard. A real-time PLC control pump system is required to ensure automatic monitoring, precise control, and rapid response to changes in pressure, flow, and storage levels. So moving on to the objective, the first one is to design and implement a PLC control pump system that ensures stable pressure and flow rates in offshore oil pipelines. The second one is to develop a real-time PLC feedback system that automatically adjusts pump speed and valve operations based on pressure and flow variations.
Hi, I'm Kesha Vartini. Today, I'm presenting our offshore oil rig pump control system, a PLC-based solution designed to ensure both performance and safety during oil extraction. The system continuously monitors oil flow, maintaining 1,400 liters per minute. If the flow drops below 1,000, the PLC activates a variable speed drive to restore the optimal levels. For pressure control, the pump operates at 4,400 psi. If the pressure exceeds 4,500, the PLC opens a bypass valve, and if it reaches 6,000, an emergency shutdown is triggered to prevent damage. In summary, our solution delivers reliability, safety, and precision, which is critical for our successful offshore operation.
At the heart of our system are the two critical sensors. First, the flow rate sensors continuously measure oil flow, maintaining our target of 1,400 liters per minute. Should the flow drop below our 1,000 liter per minute threshold, the PLC springs into an action. Equally crucial is our pressure sensor, monitoring pipeline integrity at 4,400 psi. It triggers safety protocols at two levels. First, by activating bypass valves at 4,500 psi and initiating emergency shutdowns if pressure ever reaches 6,000 psi. These sensors feed real-time data to our PLC, which makes intelligent decisions. When the flow drops, it engages the variable speed drive to ramp up the pumping. For pressure controls, it follows a tiered response. First, diverting flow via bypass valves, then, if needed, executing full shutdown. We've built in manual controls too, the start and stop switch, which gives operation direct pump control, while the manual override bypasses automation when human judgment is needed. Our safety threshold are random. The 1,000 liter minute flow minimum ensures we maintain extraction efficiency. Then the 4,500 psi warning gives operators time to respond, while the 6,000 psi emergency cutoff provides absolute protection against catastrophic failures.
Now, let me walk you through the control components that make our offshore pump system both responsive and reliable. The flow rate control continuously compares actual flow against thresholds, automatically adjusting motor speed through the variable speed drive to maintain optimal performance. Our pressure control acts as the system's safety guardian, monitoring pressure 24/7 and activating bypass valves or emergency shutdowns when thresholds are exceeded. For operational flexibility, the manual override gives engineers direct control when special circumstances demand human intervention. Finally, the pump stop control serves as the system decision maker, initiating or halting operation based on real-time flow and pressure data. Let's examine the critical output components for our offshore pump control system. The variable speed drive adjusts the pump motor speed in real time when flow rates drop below threshold, ensuring consistent performance. Our pump motor responds dynamically to PLC commands, starting, stopping, or changing the speed based on the both flow and pressure conditions. For safety, the pump bypass valve activates automatically when pressure exceeds safe levels, diverting excess flow to protect the system. In emergency, the PLC issues a pump off command, immediately shutting down operations when pressure reaches its critical threshold. Lastly, let's dive into the timer components of our offshore pump control system. First, the pump pressure timer. It tracks how long pressure exceeds the safe threshold. If high pressure persists, it triggers action like opening the bypass valve, preventing sudden surge. Next, the on-time delay timer adds a brief pause before activating the variable speed driver or shutting off the pump. This avoids unnecessary triggers from temporary fluctuation. Finally, the count up timer monitors elapsed time until pressure reaches critical levels. If pressure stays dangerous, it ensures a shutdown occurs before damage can happen.
Hi, my name is Ravin, and now I'll be talking about the results and discussion part for our project. So in rung 1, we have the start conditions for pump motor. As the pump start push button is pressed and the pump manual override is not active and pump condition is not active, the pump motor is activated. Next, we have the variable speed drive activation. As the pump flow rate is lesser than the pump flow rate threshold, the pump motor is running and the VSD is turned on. The VSD activation delay is controlled by an on delay timer. Next, for rung 3, we have the pump flow rate counter. As the variable speed drive is active, the pump flow rate incrementally increases. And for rung 4, we have the pump pressure time activation. As the pump motor is open and the pump pressure timer is closed, the pump pressure timer starts introducing a delay before pressure monitoring. Next, we have rung 5 for the pressure counting mechanism. So as the pump pressure timer is open, it activates the pump pressure counter, tracking the pressure over time. Next, we have the pump bypass valve activation as a safe threshold. While pump pressure is greater or equal to the pump pressure safe threshold and the pump bypass valve is closed, the pump bypass valve opens to relieve excess pressure. Next, for rung 7, we have the emergency pressure shutdown. When the pump pressure is greater or equal to the pump pressure emergency threshold, the pump off condition is triggered and shutting down the pump. And finally, for rung 8, we have the manual overrides. When the pump manual override is activated, it resets the pump pressure timer, variable speed drive, and pump flow rate. Thank you. Next, we have the business and economic consideration. So by implementing our PLC automation system, we can prevent excessive wear and tear because it improves operational efficiency, decreases manual intervention, and increases equipment lifespan, such that can avoid unplanned downtime. This is because we are putting in the automated shutdown mechanisms, which also increases productivity and profitability. Next, we can also conserve energy as we are ensuring that the motor and the pumps run only when required, which can also cut electricity costs. Next, we have increased customer satisfaction. This is because it enhances the process dependability and product quality. And finally, can increase business gain. This is because of the reduced operating expenses and higher return of investment ROI.
Hello everyone, I'm Munish Nachepa with the student ID of 20001267. So, thank you for your attention for all this while of this video, and to conclude, our investigation into PLC control pump control systems clearly demonstrate that these systems offer a robust, reliable and automated approach for managing critical parameters such as pipeline pressure, flow rates and storage tank levels. By integrating real-time sensor data with advanced PLC-based control logic, we can achieve optimal pump performance while minimizing the risks of unexpected equipment failures. These inherent benefits of ladder logic programming are evident that it reduces human error, limits the need for manual interventions, and enables precise sequencing and rapid fault detection. This high level of automation not only improves the operational safety but also enhances the overall system efficiency. The capability to automatically adjust the operational parameters based on real-time inputs translates into better energy management, reducing operational costs and increasing the production stability. For example, the deployment of PLC control pump control systems represents an intelligent and sustainable solution tailored to meet the demanding requirements of offshore oil rig operations. By ensuring smooth operations and reinforcing safety and environmental compliance, such systems like this can pave the way for more resilient and forward-thinking industrial framework. Thank you for me. Hello again. Moving forward, several key recommendations can further enhance the effectiveness, the dependability, and the cost efficiency of our PLC-based control systems. First, we should integrate the advanced sensor-based monitoring with the real-time data collection. This will enable precise management of temperature, flow, and pump operations, and also support the predictive maintenance strategies. By detecting the potential issues before they lead to failures, we can actually reduce the unplanned downtime and improve the overall equipment performance. Next, implementing the SCADA systems or IoT-enabled remote monitoring is essential. These technologies provide continuous real-time insights into system performance, enabling us to track the energy consumptions, identify the operational anomalies, and make data-driven decisions that bolster the efficiency. This digital layer will not only help in monitoring but also in optimizing the system parameters to match the varying operational demands. Another recommendation is to incorporate the adaptive control logic. With adaptive control, our systems can dynamically modify the motor speeds, cycle times, and in response to real-time demand changes. This flexibility is key to reducing the energy consumption and lowering the operating costs while maintaining the system responsiveness. Additionally, robust fault detection and alarm systems should be integrated into this project as well. These systems will alert the operators to potential malfunctions early on, while redundant backups, emergency stop mechanisms, and fail-safe processes safeguard both the personnel and also the equipment. Finally, to further enhance the energy efficiency and sustainability, we recommend the adoption of variable frequency drivers, also known as VFDs, energy efficient motors, and also the optimal scheduling algorithms. These measures not only minimize the wasteful operation but also ensure that the compliance with the stringent environment and the industry standards through the automated tracking and reporting. So, implementing this recommendation will maximize the return of investment, extend the longevity, and also to create a future-proof industrial automation framework, ensuring that the offshore operations remain safe, efficient, and sustainable for the future. Thank you.
Hi, I am Yuvanish Shiva, and today I'm going to explain and demonstrate the PLC circuit for the oil gathering manifold transport pump system. So first of all, in the first round we have a pump start push button, then a pump manual override switch and a pump off switch that are both typically closed, which I will explain later, and there's a pump motor output at the end. So when the pump start push button is pressed, the pump motor is activated and it starts running. The two primary operating parameters that we are currently monitoring from this pump is the pressure and the flow rate. So for flow rate, what we have done here in the PLC programming is we have set it in a way where the flow rate is initially set at 0 liters per minute and there's a minimum threshold value of 1000 liters per minute. And we have used the compare function where as long as the flow rate is lesser than the minimum threshold value of 1000 liters per minute, a variable speed drive is activated. So what does a variable speed drive do is it increases back the flow rate of the pump to operating conditions which is equal or above 1000 liters per minute. So how the variable speed drive works is we can see from rung number 2 and rung number 3. We have used an on delay timer with a time of 2 seconds, and there is a count up function to increase the flow rate of the pump by 100 liters per minute every 2 seconds. And as for pressure monitoring, we can see from rung number 4 and rung number 5 that we have programmed it in a way where the pressure keeps rising as the pump motor works. This is just to replicate extreme conditions. So how this is done is we have used an on delay timer with a time of 0.5 seconds and a count up function in rung number 5 to increase the pump pressure by 100 psi every 0.5 seconds. And we have two threshold values here, which is the safe threshold value of 4500 psi and an emergency threshold value of 6000 psi. So when the pump pressure reaches or exceeds the safe threshold value of 4500 psi, the pump bypass valve off function is still typically closed, but the pump bypass valve function is now activated. So what a pump bypass valve does is it is supposed to reduce back the pump pressure back to operating conditions. But in case where it fails and the pressure keeps rising, it might reach or even exceed the emergency threshold value of 6000 psi. So in case where this happens, the output will be the pump bypass valve off function is now activated. So this will turn off the pump bypass valve in rung number 6, and the pump off function is also activated. So for this we have to look back at rung number 1. So in here the pump off switch is now still typically closed, but when the pump off function in rung number 7 is activated, the pump off switch will now become open, and this will turn off the whole system including the pump motor. Finally, we have the pump manual override button, which manually overrides and shutdowns the whole system. What it does in rung number 8 is it activates the pump manual override function, which is still typically closed in rung number 1, but when the function is activated, the manual override switch is now open, which turns off the whole system including the pump motor. And what it also does in rung number 8 is it resets all the parameters such as the pump pressure timer, variable speed drive, and also the pump flow rate. Now I'm going to demonstrate the PLC programming to you. So as we can see here, the pump flow rate and pump pressure are all set initially to 0. The pump flow rate threshold is set at 1000 liters per minute. The units are all in times 10 above 2. The pump pressure safe threshold is at 4500 psi, and pump pressure emergency threshold is at 6000 psi. So now when I press the pump start push button, what happens is the pump flow rate starts increasing by 100 liters per minute every 2 seconds, and the pump pressure starts increasing by 100 psi every 0.5 seconds. So since the flow rate is now still under the threshold value of 1000 liters per minute, we can see from rung number 3 that variable speed drive is blinking and it is increasing the flow rate. So let's wait until it reaches 10, and there we go. So now since it has reached 10, the variable speed drive in rung number 3 has stopped blinking because it is not active anymore, and the flow rate is also not increasing anymore. So for pressure monitoring, we can see that rung number 4 and rung number 5, the pump pressure is now being increased by 100 psi every 0.5 seconds, but it has yet to reach the safe threshold value of 4500 psi. So we can see in rung number 6 that the pump bypass valve off switch is still typically closed, but the pump bypass valve function, which is the output, is yet to be activated. So we have to wait until the pressure value reaches 4500 psi. And there we go, now it has reached 4500 psi, and the pump bypass valve function is now activated. The output is activated. And we can now wait until it reaches the emergency threshold value of 6000 psi, and there we go. Once it has reached 6000 psi, we can see that the pump bypass valve off function is activated. What it does is, when we go back to rung number 6, the pump bypass valve off switch was typically closed, but now it is open. So it turns off the pump bypass valve. And also back to rung number 7, there is a pump off function that is activated at the end as the output. And we can go back to rung number 1 for this. So the pump off switch was initially closed, was typically closed, and now it has been open, and it turns off the pump motor, and it turns off the whole system. And finally, we have the pump manual override button. So as we can see from here, when the system is running and we have an emergency, let's say, we can just press this manual override button and it will put the whole system on hold and reset back all the operating conditions parameters back to 0. And finally, we have the pump manual override button. So as we can